Hey genius, welcome back to the lecture 5 of the series Periodic Table and Periodic Trends. In the previous video, means lecture 4, which is divided into 3 parts, we have discussed about the mnemonics for S block and P block elements in the part A, mnemonics for D block elements along period in part B, and mnemonics for D block elements along group, and mnemonics for F block elements in part C. All these mnemonics I have covered in both Hindi as well as English language. So if you have not seen that video, please go and see those videos. I hope that will help you to remember the elements in a periodic table. In this lecture 5, which is going to be a lengthy lecture, we are going to cover a lot of things. So we will start with showing the drawing of periodic table and what are the things you need to remember that will be helpful. And then we will show the trick to find out the period and group of a given atomic number. We will also discuss the concept of isotope, isotone and isobar. Then we will discuss the filling of electron, orbit and orbital concept, and Aufbau principle for the filling of electron. And at the end, I will also show a tricky way how you can easily remember this Aufbau principle, which orbital will be filled first and then which orbital will be filled. So there is a simple way to remember it. Thereafter, we will discuss nomenclature of super heavy elements, trivial name of different elements, lanthanide and actinide contraction. After that, we will discuss Slaughter's rule and determination of shielding constant of electrons based on Slaughter's rule. And towards the end, we will discuss Goldsmith's geochemical and cosmochemical classification of elements based on chemical affinity. So these many things we are going to cover in this video. So without wasting any time, let's start. So this is going to be the image of a complete periodic table. This periodic table I have in my room, and you may have a different periodic table, but there are some minor details that you need to know, or color coding and different scheme coding that you need to know, that what this periodic table, what kind of information this is providing. So in your periodic table also you can find a small indexing from which you can know what are the informations given in the periodic table. I have already discussed about this indexing in the previous videos. You can go and check that what are the informations hidden in the periodic table. So as we know, in the periodic table we have 7 periods and 18 groups. So these rows are called periods and we have 7 periods, and these columns are called groups. So we have total 18 groups. Now group 1 is called alkali metals. Group 2 elements are called alkali earth metals. Now here group 11 elements are called coinage metals. Group 15 elements are called nitrogens. Group 16 elements are called chalcogens. Group 17 elements are called halogens, and group 18 elements are called noble gas. Now this group 1 and 2, these are actually S block elements. Group 13 to 18, they are P block elements, and in between them we have group 3 to group 12, these are D block elements. And inside this D block, in this space, we have these F block elements. Now when I used to practice remembering this periodic table, so I used to write all these elements with their atomic number, and some of the atomic weights I used to remember. For example, till from hydrogen to calcium, I used to remember both the atomic number and atomic weight. And after that, I used to remember atomic weight for iron, copper, zinc, bromine, here iodine, and you can see some more elements, for example mercury, lead, So these elements which we are going to come across very soon, very frequently in our chemistry practical or any other fields. So for that, I used to remember these atomic weights. Now, as you know, this group 18 where we have this noble gas elements. So these are the atomic number for those noble gas elements. Now we have to remember these numbers because based on these numbers we can find out the period and group of any given atomic number. So how to remember these things? So first and foremost we have to remember this, and I will take a pen here. So we have to remember that element 1 and 2, those two elements are in period 1. Now from atomic number 3 to 10, those elements are in period 2. Now from atomic number 11 to 18, those elements are in period 3. From 19 to 36, those elements are in period 4. From 37 to 54, those elements are in period 5. So from 55 to 86, those elements are in period 6. And from 87 to 118, those elements are in period 7. So we have to remember these numbers. So if we remember these numbers, we can easily find out the group and period. For example, let's take zinc, the case of zinc. So its atomic number is 30. So 30 comes in between 18 and 36. So here 30 comes here. So if we remember this numbering, from there we can count, that is 1, 2, 3 and 4. So zinc or element or the atomic number 30 will be an element which is housed in period 4. Now how to find out the group number? To find out the group number, you have to subtract the previous inert gas element's atomic number from the given atomic number value. For example, if you are given atomic number 30, so your A is 30, so you have to do A minus this previous inert gas element. So I will write A minus I. Now as A you are given 30, so you have to do 30 minus, and the previous inert gas has atomic number 18, so I will just subtract 18 from here, and I will get 12. So this element will be in period 4, group 12. So for that you just have to remember these inert gas elements atomic numbers. If you remember that, you can easily calculate the period and group of any given atomic number. Now how to remember these values? To remember these values, you have to take help of your ideal life story or your ideal love life. For that, you can think that you are in love with a girl and two of you know each other since last 10 years. So what? Two of you madly love each other and you guys know each other since last 10 years. And when your girlfriend became 18, you guys get married. And at the age of 36, you have a happy family, two of you and your children. And at the age of 54, you have become grandparents. You have son and daughter and their son and daughter. You have grandchildren. And 86 is the age where you do coffin dance from staying inside the coffin. For example, Yeah, I will just draw the sign of death. So the god of death comes and takes you at the age of 86. And when you were dying, so that time 118 people were there who were grieving at your death. So that's how you can remember these elements atomic numbers. Two of you love each other since last 10 years. You guys get married at the age of 18, at the age of 36 you have a happy family, and at the age of 54 you have grandchildren and you have enlarged the family. At the age of 86 everything is over and you pass away. At that time 118 people came to your last journey. So this is how you can remember the atomic numbers of the noble gas elements. And another thing I can say this, see this one is for another small trick. So this one is fourth period. So this one will be, just a second. So this one is the fourth period. So this is actually 40 minus 4. 40 minus 4 you will get 36. This one is the fifth period. So this one is actually 50 plus 4. And this one is, although the sixth period, you will do 90 minus 4. 90 minus 4. So yeah, if you get confused whether it is 36 or 38, whether it is 56 or 54, that time you remember this thing, that this one is 40 minus 4, this one is 50 plus 4, and this one is 90 minus 4. So this is how also you can remember these three values. And these two are easy. This is 18. You just add 100, you will get 118. So these two are also easy. Next, we will discuss about the concept of isotope, isotone, and isobar. So these three are actually very confusing terms, but very simple to remember if you know what is the basic difference between these three terms. So isotopes are actually same elements that contain equal numbers of protons but different numbers of neutrons. So in isotope, your proton number is same, but the neutron number is different. So in nucleus, for example, if you take hydrogen, here we have one proton and no neutron. Here we have one proton, one neutron. So this is called protium, this is called deuterium, this is called tritium. Here you have one proton and two neutron. So these three elements are called isotopes to each other. Here number of proton is same, but number of neutron is different. So these three are called isotopes. Now in case of isotone, so elements that have same number of neutrons and differ in the number of protons. So in case of isotope, we have same number of proton, different number of neutron. Here it is exactly opposite. So you have different number of uh, proton, but the same number of neutrons. So these are called isotone. For example, if you take O16, N15 and C14, so in case of that we have different number of protons but we have same number of neutrons. So these are called isotone. Again, if you see silicon and phosphorus, we have different number of protons. Here we have 14 and here we have 15, but we have same number of neutron, that is 16 in both the cases. So these are called isotone. Whereas in case of isobar, we have different elements. That means the number of proton is different, but we have same atomic weight. Now atomic weight is a summation of number of protons and number of neutrons. So we have different number of protons, but we have same atomic weights. So that means we have both the proton and neutrons different, but the atomic weight is same. For example, if you take this argon and calcium, so here we have 18 protons and 22 neutrons, whereas in case of calcium, we have 20 protons and 20 neutrons. See, both the protons, number of protons and number of neutrons, both are different. But this atomic weight, which is 40, that is identical. So we have only same atomic weight. So that's why these are called isobar. Here we have some more examples. You can take this one, cerium or selenium, cerium 76, selenium 76, or you can have this iron 58 and nickel 58. You can have argon 40, potassium 40, or calcium 40. And if you get sodium 24, magnesium 24, cobalt 64, nickel 64, these are all the pairs that are isobar to each other. So just a quick recap. In case of isotope, we have same number of protons but different number of neutrons. In case of isotone, that is exactly opposite. We have same number of neutrons but different number of protons. And in case of isobar, both the number of protons and neutrons are different, but we have same atomic weight. Now let's see some examples of isotopes. So we have already discussed about the isotopes of hydrogen in the previous slide. Let's see it again. So we have these three isotopes of hydrogen. In protium, we have only proton, there is no neutron. In deuterium, we have one proton, one neutron. And in case of tritium, we have one proton and two neutron. Now in case of carbon, we have carbon 12, carbon 13 and carbon 14. So if you see carbon 12, we have 6 protons and 6 neutrons. In case of carbon 13, we have 6 protons and 7 neutrons. And in case of carbon 14, we have 6 protons and 8 neutrons. Now let's see the isotopes of oxygen. So we have oxygen 16, oxygen 17 and oxygen 18. So in case of oxygen 16, we have 8 protons and 8 neutrons. Whereas in case of oxygen 17, we have 8 protons and 9 neutrons. And in case of oxygen 18, we have 8 protons and 10 neutrons. So these pairs are called isotopes to each other. Now let's see the IUPAC periodic table of the isotopes. So I will recommend you that you go in that website and you check this periodic table of the isotopes. So in this periodic table, it is given that one element, how many isotopes are there for each and every element. You can see these wheels. So the number of segment of these wheels tells how many isotopes are there. And you can see the color coding as well. Here the color coding is not properly visible. You can go and watch from the website that what is the meaning of these colors, different colors, pink, yellow, blue, white. So I will strongly recommend you that you go and just take a look of this IUPAC periodic table of isotopes. Next, we are going to discuss about the filling of electrons in an atom. The first thing is that the number of electrons, how many electrons we have, that determines the number of orbits. Depending upon the number of electrons, the number of orbit will be determined. And the number of protons, depending upon the number of protons, the electrostatic interaction between the nucleus and the electrons will differ. So if you have more number of protons, the electrostatic interaction will increase, and when you have lesser number of protons, the electrostatic interaction will decrease. For example, you can see here in case of hydrogen, we have one proton and one electron here in first orbit. In case of helium, we have two protons and two neutrons in the nucleus, and we have two electrons in the first orbit. In case of lithium, we have three protons and four neutrons. You see, these red ones are the protons and these blue balls are the neutrons. So we have 3 protons and 4 neutrons, and we have 2 electrons in the first orbit, this one and this one, and another 1 electron in the second orbit, this one. Now in case of beryllium also, the next electron also comes in the second orbit. So now we are going to see, we are going to learn how these electrons will come and how many electrons we can fill in orbitals. So those things we are going to learn. So if you see this diagram, so first we have hydrogen. In case of hydrogen, we have only 1 electron. That 1 electron will come and fill in this first orbit. I'll make a cross sign to determine to denote the electrons. In case of helium, we have 2 electrons and both the electrons will be filled in the first orbit. 1 electron here, another electron here. Now in case of lithium, when we add another electron, so first 2 electrons will go in the orbit number 1. You can see here, first 2 electrons will be filled in the first orbit. Now the next electron, the third electron, will be filled in the second orbit. Now one by one we will put electrons in the second orbit, and you can see after that lithium we will get beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And let's see in the case of neon. So in the case of neon we have 2 electrons here, 1, 2, and we will have 8 electrons. One by one we have put 8 electrons in the second orbit. 3, 4, 5, 6, 7 and 8. So in case of neon, first 2 electrons are in first orbit and next 8 electrons are there in the second orbit. Now when we have another electron coming in case of sodium, so that 1 electron will actually occupy the third orbit, and then we will put 1 by 1 electrons in the third orbit. So as you go along this period, you put 1 by 1 electrons in the same orbit, and after this inert gas, when you put one more electron, that electron goes in the next orbit. So here you can see the putting of electrons here. For example, here in the hydrogen there is 1 electron. In helium we have put 2 electrons. Now when we add another electron in case of lithium, that goes and takes the second orbit. Now we put electrons 1 by 1 in the second orbit. 5 electrons in case of nitrogen, 6 electrons in case of oxygen, 7 electrons in case of fluorine, and 8 electrons in the second orbit in case of neon. And then when we want to put one more electron, that will go and take house in the other orbit, third orbit. And again we will fill electrons here, and in case of argon we will have 2 electrons in the first orbit, 8 electrons in the second orbit, third again 8 electrons in the third orbit, and again when we put one more electron in case of potassium, that will go and fill the fourth orbit. So likewise we fill electrons one by one in one atom. This is just for conceptualization. Now we will go into more details. Before that, if you see the periodic table of elements, atomic radius, so this periodic table gives you the size of the elements. If you see these left ones, they are in bigger size, or these spheres are bigger in size. That means their atomic radius is bigger. And as you go along a period, here from left to right, the size decreases. Now why it happens? So from left to right, when we are going, now we are putting more and more electrons as well as protons. From left to right, the number of proton is also increasing. So when we increase the proton number, so that time the electrostatic attraction between the nucleus and the electrons increases. So as the attracting power increases, so it's like a, see, we have proton here, and then surrounding it we have electrons, right? This, sorry, I'll erase it. Just a second. So we have nucleus, and then surrounding that we have electrons and different shells of electrons. Now assume this nucleus is a girl, and these electrons, those are actually boys. Now when we put more and more protons, so the girl is more and more attractive. So that time this nucleus, sorry, these electrons, means the boys, they try to come close. So these shells will come close. These orbits will try to come close because the girl is very attractive. The more number of protons are there, so as the girl is more attractive, the electrons, the boys, they will try to come close to that girl. So the orbit will shrink because the electrostatic attraction is more. The electrons will try to come close to the nucleus or the positively charged nucleus or positively charged protons. So as the girl is more and more attractive, as the number of proton is more, the electrons or the boys will try to come more and more close. So that's why the size actually shrinks from left to right in a period. These things I will discuss in detail in the next lecture, lecture 6. Do not miss that. That is a very important lecture, and I will discuss each and every periodic trend and their um, why is it happening, and the detail I will discuss in the next lecture. This is just to give you a preliminary idea that how if you increase the number of protons and electrons, so how the size will shrink, and if you increase more and more electrons, how it will be filled in the orbitals or orbits. So next we will come to the discussion of orbits and orbitals. So for this, let's think this is your home. Just let me draw a home for you. Just think this is your home, and this one over here is your school. School generally has a bigger gate, right? And all the classrooms, they have small windows. Oh, sorry, my drawing is pretty bad. So this is your home and this is your school. Now from home to school, you can go either by walk, or you can take a cycle and roam here and there, here and there, here and there. and then you can go to the school, or when your father is free, he can tell you that come son, we will go by our car today. So you can take a car and you can take a main road and you can go like this, right? So there are different possibilities. From home to the school, the distance is same, but still there are different possibilities, right? You can go simply by walk, or you can go by cycle, or you can go with your father with a car. So different possibilities are there. So similarly, for the electrons also, they have different possibilities or probabilities. So they can occupy different paths or different portions of a orbit. Now let's try to understand the definition of orbit and orbitals. So an orbit is designated as the path for electrons to revolve around the nucleus. So this is actually a two-dimensional conception, that the electron is rotating around the nucleus. So here this yellow one is the nucleus and the electrons are rotating around it. So if I draw like this is the protons or the nucleus, sorry, and in this path the electrons are circulating. My drawing is pretty bad in this one. Actually, I'm using a very bad setup. Yeah, so this one is your proton and your electron is revolving around it. So this is a two-dimensional picture, and this one here is called orbit because this is a two-dimensional thing. And I have just given or designated the path in which the electron is revolving around the nucleus. Whereas an orbital is the 3D space around the nucleus where the probability of finding an electron is maximum. So inside this same path, we have different three-dimensional space. For example, in your case, you can take different travel mode to reach to the school. Similarly, electron can take different 3D space to orbit that nucleus. So an orbital is the 3D space around the nucleus where the probability of finding an electron is maximum. So as we discussed that orbitals are the 3D space occupied by electrons where the electron density is maximum. So inside one orbit there can be different orbitals. For example, when we have orbit number 1, 2 and 3, which are also known as K, L and M. So in that case, in orbit 1 we have only one s. So that is only one orbital, one s. In case of second orbit we have 2s and 2p. In case of third orbit we have three different orbitals, that is 3s, 3p and 3d. Similarly, in the fourth orbit, we have 4s, 4p, 4d, and 4f. Now, let's see the shape of s orbital. So, s orbital is actually spherical in nature. So, this one you can see spherical shape. This is the shape of s orbital. So, electron density is almost same in the all directions, and it takes a shape of a sphere. Now, this is for 1s. So, if you go to the 2s, that will be a bigger sphere. Compared to 1s, the 2s will be a bigger sphere. Similarly, the 3s will be much bigger sphere. Now let's see the p orbitals. P orbitals are having three different compartments. So these are called px, this one is px, this one is py, sorry, this one is pz, and this one is py. Oh, sorry. So p orbital has px, Py, and Pz. These three different compartments. Now these p orbitals, they look like a dumbbell. You can see in center the electron density is 0, and as you go further from the nucleus, the electron density increases. So it actually looks like a dumbbell. So in the center the electron density is 0, and as you increase the r, go along as you go away from the nucleus, the electron density increases. So these are kind of like this, dumbbell shaped. So if there is only one dumbbell, that is p orbital, and in case of d orbital there are actually two dumbbells. So as I have drawn this shape, this looks like the d orbital. Now in case of d orbital, so we have five different orbitals. So these are named as dxy, dyz, dzx, dx square minus y square, and dz square. Similarly, f orbital, it has seven different compartments. So these things I will discuss in some later videos. I will make dedicated videos to discuss these things. But for the time being, we will see this video which I have taken from this channel scienceviz.com. I will put this link in the comment or description. If you want, you can go and check this video. It's a very nice video. From this, you can conceptualize how these electrons are revolving. Now, I'll show it. So first we have this electron. Here, this one is the nucleus, or just write P, or proton, positively charged nucleus, and this electron is revolving around it. Now in the 2D space, we can see that electron is circularly moving, but actually in the 3D space, it will be uh, it will create a sphere. So the electron density will be like a sphere. Let's see. In case of 1H, we have one proton and one electron. So the electron is circulating that proton. So in the 2D direction, we can see only like a circle, but when we see the 3D space, it is actually a sphere, and the electron density is equivalent in the entire sphere. So this is in case of proton. In case of 1H, hydrogen, only one electron. Now if we add another electron, so that means we have two protons and two electrons. We are adding another electron. In case of helium, both the electrons will occupy 1s. That's why we write 1s2 in case of helium. Now when we add another electron, that will come, and that cannot take 1s because 1s is already filled. So that will take 2s, and that we get lithium, 3 protons and 3 electrons. Now we add another electron, that will also go and take 2s. So we get beryllium, 2 protons and 2 electrons. Now when we add another electron, that goes in the p to p. In case of boron, that takes p, or it can be sp2 hybridized. This is how it will look in the sp2 hybridization. Now when we add another electron, in case of carbon, it can either take sp2 and 2p. This is the 2p and sp2, or it can become sp3 hybridization. This is how it looks when carbon is sp3 hybridized. Or it can be sp2 hybridized and one electron can be in the 2p. This is how it will look. Or it can be sp hybridized and two electrons can remain in the 2p. So this is how it will look. So there are different hybridizations. Based upon that, the electrons can occupy different 3D spaced or different orbitals. So these things, just take a note. These things we will discuss in detail for some other videos in other chapter. So that time I will discuss in details about these things. Now let's see the electronic configuration. So in case of hydrogen, we have seen that the hydrogen, the electron will go in the 1s orbital. So that we write like this. So this box means one orbital, and this one is 1s orbital. So in case of hydrogen, the first electron goes in 1s. Then in case of helium, we have two electrons. So both the electrons goes in the 1s orbital, and each and every orbital can take only 2 electrons or up to 2 electrons. When we have another electron, that will go in the 2s. Now when we add another electron, that goes also in the 2s, and these arrows actually denote spin. So for electrons you have to write like this is called up spin and this is called down spin. When we have only one electron, we write it as up spin, and when the second electrons come, we add the down spin. In the same orbital, both electrons cannot have same spin. Okay, just try to remember this, that if there are two electrons, both electrons cannot have same direction. One will be up, one will be down. So in this case, this is up spin, and when we add another electron, that electron becomes down spin. In case of boron, we add another electron in the 2p, and this one is the 2p, which has 3 orbitals, 2px, 2py, 2pz, and in total it can accommodate 6 electrons. So let's see, in case of proton, the electronic configuration is 1s1. In case, sorry, I'm saying proton, this is actually in case of hydrogen. I'm sorry. In case of hydrogen, the electronic configuration is 1s1. In case of helium, the electronic configuration is 1s2. In case of lithium, another one electron comes and that occupies 2s. So the electronic configuration becomes 1s2 and 2s1. In case of beryllium, the next electron also takes 2s. So 1s2, 2s2. In case of boron, the next electron takes 2p. So the electronic configuration becomes 1s2, 2s2 and 2p1. In case of carbon, we have 1s2, 2s2, 2p2. In case of nitrogen, it will simply become 2p3. In case of oxygen, it will become 2p4. In case of fluorine, it will become 2p5. And in case of neon, it will become 2p6. Now, in this case, 1s2, 2s2, 2p6, total electrons are 10, and it is inert gas element. After that, whenever we add another electron, that will go in the 3s. So in case of sodium, we get 1s2, 2s2, 2p6, 3s1. Then in case of magnesium, it will become 3s2. In case of aluminium, when we increase another electron, that time it goes in the 3p, and we get 1s2, 2s2, 2p6, 3s2, 3p1. Then in case of silicon, we add another electron in the 3p, and we add another electron in phosphorus, sulfur, chlorine, and argon. So again, in case of argon, the last electron is going in 3p, and we get the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Now as the 3p6 happens, so the orbital is closed. Now if we add another electron, that will go in the next orbital, that is 4s1. So in case of potassium, we get 4s1. In case of calcium, we get 4s2. So this is called the filling of electrons, how electrons are getting filled one by one, in which orbital, and which orbital will come first, which orbital will come next, that we are going to learn later in this video. So the thing you have to remember is that how these electrons are getting filled, and it cannot accommodate more than 2 electrons. The orbitals cannot accommodate more than 2 electrons. So to understand this filling of electrons, we will learn Aufbau principle. Now we have seen that in the first period we have 1s, in the second period we have 2s and 2p, or second orbit. In the third orbit we have 3s, 3p, 3d. In the fourth orbit we have 4s, 4p, 4d and 4f. Similarly in the fifth orbit we have 5s, 5p, 5d, 5f and 5g. Now when we are filling electrons, first we fill 1s, next we fill 2s, next we fill 2p and then 3s. So we are coming actually from this end. First we fill this and then we fill this. Then we fill 3p. And after filling 3p, so you cannot simply fill 3d. You have to go to 4s. And now after filling 4s, you cannot simply fill 4p. You have to actually fill 3d first, then 4p, and then 5s. So that is why this arrow. So this arrow means first we are filling 1s, then we are filling 2s, then we are filling 2p, then 3s, then 3p, then 4s, and then 3d, then 4p, 5s. This seems very hard to remember, right? So that's why you can remember this alternative path. This is how I remember this electron filling orbitals. So I remember like this s. So this is a lonely s, just one s. Now here s has p, so s is not single anymore. When it has a partner, I write square because it is not single anymore. So first it is s, then sp square, sdp square, sfdp square. Then what? Now what does it mean? So first, when the electron will come, that will fill s, and again it will be sp square, means next line it will be s and p, and again there will be another sp because it was sp square, right? So s, then sp square, now sdp square. So next line there will be s d p, and again another sdp because it was square. Next it will be sfdp square. So again next I have to write s, then f, then d, and p. Similarly I have to write another sfdp which I am not writing. Now what I will do, so this is kind of pyramidal pyramid like order, right? First we have s on top, then sp, again sp, then sdp, again sdp. Now you have to remember, so these s and p are actually ns np, means this one is the first row, right? So this one will be 1s. Now this s and p, these are in the second row, so it will be 2s, 2p. This one in the third row, 3s, 3p. And next this one is the fourth row. According to which pyramid I am writing, this one comes in the fourth row, so this one will be 4s. Now in case of d, you have to write n minus 1. In case of s and p, it will be nsnp. In case of d, it will be n minus 1d. And in case of f, it will be n minus 2f. So this one is the fourth row. So I will write 4s, and n minus 1 means 4 minus 1. So 3d, and then 4p. Now again, this one is the fifth row according to my pyramid. So I will write 5s. This one will be n minus 1. So 5 minus 1 means 4d. And again this one is the np, means 5p. And in case of this one is actually 6s. And in case of f, we have to write n minus 2. So in the sixth row, it will be 6 minus 2 means 4f. And d will be n minus 1. So 6 minus 1, it will be 5d. And again np, so 6p. So I remember this pyramid, and whenever I am doing any electronic configuration, I will quickly draw this s, sp, sp, sdp, sdp, and sfdp. So first electron will be filled in 1s, then 2s, then 2p, then 3s, 3p, then 4s, 3d, 4p, after that 5s, 4d, 5p, then 6s, 4f, 5d, and 6p. So you can remember either this above principle, you can write down, and then put these arrows to determine that where the electron will be filled first. Or you can do like this pyramidal way: s sp square sdp square s sp square sdp square sfdp square. And then when you break these squares, you have to write this in two different rows, and it will be filled one by one according to the row. So any one way you can choose to remember this electronic configuration filling or electronic filling. You can choose any way, whichever seems easy to you. Now we will discuss about the nomenclature of super heavy elements. For example, if someone says what will be the name of the element whose molecular weight, whose atomic weight or atomic number, whose atomic number will be 200, or whose atomic number will be 600 or 500, what will be the name? Now to determine these higher elements or super heavy elements, we came up with this nomenclature system. According to this, so if you see this one, 200, atomic number is 200. So first we will separate it letter by letter. First we have 2, then we have 0, then we have 0. So there is coding, nomenclature for each and every number. So for 0 we will write un, for 1 we will write nil, for 2 we will write bi, for 3 we will write tri, for 4 we have to write quad, for 5 we have to write pent, for 6 we have to write hex, for 7 it is sept, for 8 we have to write oct, for 9 we have to write n. So whenever we are saying that what will be the name of this atomic number 110, so we will separate it by number. So first there one number, then another one, then 0. For 1 we will write un. First for 1 we are writing this un. For another one we are writing another un, so another un. And for 0 we have to write nil, so we are writing nil. And at the last you have to use yum, ium or um. If I is already present, you have to write um. I think this there will be I here. So again, let's see for 117. If you see 117, for 1 we have to write this un. For another one we have to write another un. And for 7 we have to write sept, and then we will add this suffix yum. So the name will be unseptium. Similarly, now we will do the atomic number 200. So for 2 we will write bi, for 0 we will write nil, for another 0 we will write another nil. So we will get bi nil nilium, right? Let's take this one, 109. For 1 it will come un, for 0 there will be nil, and for 9 we have to add n, and at the end we will add suffix yum, ium. So the name will be un nil n yum. Fine. And this symbol will actually take the first letter of each numerical root. For example, if you see for atomic number 200, binilnilium, so in the bi the first letter is B, and in case of nil the first letters are N, so it will be B and N. Similarly, in case of 109 anilenium, it will be U N E, the first letters of these roots or codes. So this is how you do the nomenclature of super heavy elements. So you don't have to assign any name. You can just simply call it by its atomic number. Now we will discuss about the trivial names of different elements. So the alkali metals So the group 1 metals are called alkali metals. Now hydroxides of these metals are strongly alkaline. So that's why these group 1 elements are called alkali metals. Now group 2 elements, those are called alkaline earth metals. So the substances that remained unchanged by fire were called earths by the ancient chemists. The oxides, that is lime, magnesia, strontia, baryta, these actually refer to the earths, and these oxides are alkaline in reaction. So these alkali earth metals or the group 2 elements, their oxides are also uh, alkaline in nature. So thus the term alkaline earths actually refers to the oxides of the metals. It may be noted that barium oxide is amphoteric. So in this group 2, the exception is the barium oxide, whose oxide is the exception is the beryllium, whose oxide is the amphoteric in nature. Other than that, the rest of the elements, they make alkaline oxides. That's why the name of this group is alkaline earth metals. Now group 16 elements are called chalcogens. Greek word chalkos means copper. I'll just take this laser pointer. Greek word chalkos mean copper. In nature, copper is usually found associated with sulfur and its congeners. So that's why we call these group elements or 16 group elements which contains sulfur and the other elements, we call them by chalcogens. Now elements of group 17, those are called halogens. So Greek word halogen means salt producer. Element of this group react with the metals to produce ionic halide salts. This justifies the name halogens. So in fact, the term halogen was first given to chlorine for its forming ability, for its salt forming ability with the metals. The term was subsequently extended to all members of the group. Now we have noble gases or inert or rare gases. So group 18 elements are called noble gases. They are named so for their chemical inertness. Because they are chemically inert, they don't react with most of the elements. That's why they are called inert gases or noble gases. Lanthanum series. So the elements from lanthanum to lutetium are called lanthanum. So it is named so because the chemically similar elements appear after lanthanum. So after lanthanum till lutetium, all these elements are chemically similar. So that's why they are named from the name of lanthanum, and they are called lanthanum series or lanthanides. Next, lanthanides or lanthanoids or rare earths. So cerium to lutetium. So the word earths refer to the oxides, and in fact these elements were first discovered as their oxides. So this is why these were called rare earths. So however, these are not rare and they occur widely in nature, usually together. Similarly, we have seen alkaline earth metals. So those were also available in oxide forms. Similarly, these are also discovered in their oxide forms, and these are called uh, rare earth metals. Now, actinum series, actinum to lawrencium, these are called actinum series. Actinides or actinoids, from thorium to lawrencium, these elements are called actinides. Now, lawrencium was originally represented by Lw, but now as per IUPAC recommendation, it is presented by Lr. Now we will see the coinage metals, copper, silver and gold. These are in group 11. So these are called coinage metals. So these are known as coinage metals because of their former uses in making the coins used in primitive currency. So in earlier days, when a human used to make coins or currency, they used to use these metals, copper, silver, and gold. Platinum metals, so ruthenium, rhodium, palladium, osmium, iridium, platinum. These group 7b in the Mendeleev's periodic table, or group 8, 9, and 10 elements, these are called platinum metals. So in this family, platinum is the oldest one, and it is also the most abundant one in this family. Its chemistry is also most extensively studied among the members. This is why the whole family is known by its name. Noble metals, so platinum metals, gold, silver, and mercury, these elements are also known as noble metals. Transuranium metals, so elements after uranium is called transuranium metals. Now we will discuss about another major topic, that is lanthanide and actinide contraction, which is also known as F contraction. Now what is this? So if we consider lanthanides from cerium to lutetium, or actinides, which is from thorium to lawrencium, their atomic and ionic radii gradually decreases along the series with the increase of atomic number. So if we go from left to right in these lanthanides, the atomic radius and ionic radius decreases very much. So this is called F contraction, or lanthanide and actinide contraction. The same trend can be also observed in case of D block elements. So this D contraction is known as Scandite contraction. Now let's see what are the reasons. The reasons are poor shielding power of n-2f orbitals, and you can also see relativistic contraction of ns orbital. So I will try to explain it. Let's see. This one is your, sorry, let me draw it. I'll just give you a basic idea about this. So this one is our positively charged nucleus. Think it as of an attractive girl, and there we have different layers of electrons, different orbits. Now we have some electrons here, some electrons here. Now try to understand. So the poor shielding power of n-2f orbitals. So let's suppose we have some electron here and here. Now these electrons, let's consider these are the f electrons, n-2f electrons. Now these electrons, if they don't charge this positive charge, so this positive charge is showing some attraction. It is attracting all the electrons, right? Now it is attracting this one, this one, this one, this one, all of these electrons. Now these previous electrons, they are screening the positive charge of the proton. Now if they fail to screen that, if their shielding power is not good, then this proton will have higher attraction to this electron, to this outermost electron, right? Now just forget all these things. Now consider these two. These are the f electrons. Let's consider it as f electrons, and these are the next maybe s or p electrons. Okay, now these f electrons, if they have stronger shielding power, that means if they can uh, they can reduce this attraction of this nucleus to these electrons, that time we will say that these electrons have stronger shielding power. But actually these f electrons, those are actually diffused in nature, and they have very less shielding power. So that's why the attraction of this nucleus to this outermost electron increases. Now let's try to understand it in simple words. For example, this is an attractive girl, and these are the some uh, lovers of that girl. Okay. Now if these lovers, they don't have money, if they don't have sufficient money, then this girl will go for other boys, right? Now if this boy has money and these f electrons or f boys, they don't have money, then this girl will give importance or will get attracted to the other boy, this outermost boy, right? So the girl will try to make him close, the rich boy, which is in s or p orbital here. Again, I will try to explain. So these are different boys. If those boys, they will not read much, they will not get educated, then they will not get good job, they will not have money. So then this girl, this attractive girl, will not be interested in these boys. So that time this girl will get attracted, or that girl will attract these boys, these s and p orbital boys, which have good job and they have good money. Similarly, in the electronic world, if this f electrons, they are actually diffused in nature, they cannot shield this attraction of this nucleus to these electrons, to the outermost s and p electrons, because these f electrons are diffused in nature. So that poor shielding power of n minus 2 orbital electrons, because of that these electrons get attracted and this radius actually decreases. Now these orbits or orbitals gets shrinked. The entire orbital or the radius RDF or radial distribution function of this orbital gets shrinked. Because of that, these electrons come closer, the atomic and ionic radius of these f block elements decreases, because this f electron, they are not reading properly, they are not putting their effort in reading, and that's why they have lesser shielding power. That's why you all please read properly, be properly educated, and whatever you will do in life, it will be great. So take a proper education. Don't be like this f electrons, okay? Then your girl will also get attracted to the other s and p electrons. So because of this, as these other x and p electrons, they experience higher attraction towards the nucleus. So that's why there is a relativistic contraction of ns orbital. So this orbital contracts and the size of the atomic and ionic radius decreases. So these are the reasons. These are the main two reasons behind F contraction. Now what are the results? So 5D members are almost similar in size to the 4D members. So the same kind of contraction happens in the D block elements also, which are known as Scandite contraction. Because of that, so the 5D members and the 4D members are in the similar size. Actually, the 5D members should be bigger in size because they have additional uh, orbit, but still it is almost similar in size. Now the size is same, but the atomic number is more, atomic weight is more, so that's why the density gets increased. So the high density in the post lanthanides, and due to the enhanced effective nuclear charge experienced by the valence shell electrons, post lanthanides are noble elements. Now this point let's try to understand. So you see this nucleus that is attracting these electrons, these furthermore these valence electrons. So now these electrons are having higher affinity to the nucleus. So that's why these electrons will not be get lost. So you cannot simply just remove this electron. You cannot easily remove these electrons. So that's why it is difficult to remove these valence electrons in case of noble elements, and that's why they are not reactive. Now reaction is nothing but exchange of electrons. So because the attraction is more, it will not easily get lost. The electron will not get easily exchanged. So that's why these elements are called noble elements. Now let's see some other results. Due to greater effective nuclear charge, post-lanthanides have abnormally high electron affinity. The electron affinity is high because you can put more and more electrons as the electrostatic interaction is higher, so it can accommodate the electrons. Now because of F contraction, covalency increases from lanthanum to lutetium. So as the size becomes smaller and smaller, um, it tries to make covalent bond from lanthanum to lutetium. If you go, it tries to make covalent bond. It will not try to make ionic bond because it will not try to give up the electrons which are tightly bound. Now covalency proportional to acidity of oxides. So acidity also increases from lanthanum to lutetium. Next is the thermal stability of carbonates and sulfates decreases from lanthanum to lutetium. Standard reduction potential of M3 plus to M increases from lanthanum to lutetium. So these are the results which are occurring due to this lanthanide and actinide contraction. So take a note of this thing and just try to understand that this nucleus is like an attractive girl because these F electrons, they have not read properly during their class or during their uh, courseworks. That's why these F electrons are diffused in nature. They have very less shielding power, they have very less money. So this girl is attracted towards the other electrons, sp electrons, outermost electrons. And because of that, there is a relativistic contraction in this orbit or orbital, whatever you say, and those elements will become inert in nature. Hope this idea is clear. This is a difficult to understand. This idea is little bit tricky to understand. If you are lower standard, if you are in a lower standard, then you just note down the points. Maybe when you will go in your bachelor's or master's, that time you will get to know these things. Next, we will discuss Slaughter's rule. Now, this rule provides the numerical values for the effective nuclear charge in many electron atoms. It was formulated by John C. Slaughter in 1930. I'll take the laser pointer here. Sorry. So, according to this formula, Z effective is equals to Z, which is the atomic number of that molecule, minus S. S is the shielding constant. So, how to determine the S? So, to determine the Z effective, we already know the Z, the atomic number of the atom, and we just have to determine this shielding constant S. So, firstly, electrons are added according to their principal quantum number. Remember, not following the Aufbau principle. Okay, they will just simply grouped according to their principal quantum number and taking S and P in the same shell. So the order will be like that: first we have 1s, then 2s and 2p in the same shell, 3s and 3p will be in the same shell, and then will come the 3d. So according to the Aufbau principle, after 3s and 3p, 4s will get filled, right? But here we are not following the Aufbau principle. Okay, in case of Slaughter's rule, you don't follow the Aufbau principle. You just arrange it and then calculate. So 3s, after 3s and 3p, you will put 3d. Then again you will put 4s and 4p together. then you will put 4D, then you will put 4F. So D and F are separately. Only S and P you can put together. Okay. D, F, G, these things you will put separate. Then you will again put 5S and 5P. Then you will put 5D and then 5F. Now let's see the quantitative value of this shielding constant. Okay. So the shielding constant for each group determined as, the first one is an amount of 0.35 from each extra electron within the same group. So if the electron for which you are counting the shielding constant, it is sharing the house with other electrons, so you have to calculate 0.35 for the other electrons. Okay, and 0.30 for only 1s electron. In 1s it will be 0.30, other than 1s it will be 0.35 from the same group. So these ones are called actually groups. This one is one group you have created, this one is another group, this one is group. You have grouped the electrons for determining this shielding constant. If the electron which is to be considered is in ns or np, this group, so an amount of 0.85 from each electron with principal quantum number n-1 and an amount of 1 for each electron with the principal quantum number n-2 or lesser. Now next, if the considering electron is in D group or F group, an amount of 1 for each electron, those having smaller principal quantum number and same principal quantum number but smaller azimuthal quantum number or different group. Now we will try to understand it from the example, taking the example. So first, this is the summary, or this is the chart. Here are different groups, and here you can see for the other electrons in the same group what will be the shielding constant value. From other electrons in the same principal quantum number but different azimuthal quantum number, from other electrons with n-1 quantum number, and from all other electrons up to n-2 quantum number. For 1s we have maximum 2 electrons, so we have just 0.30 from the other electron in the same group. And for other ns and np we can have total 8 electrons here. So for other electrons in the same group you have 0.35, and for other electrons with n-1 quantum number you have to add 0.85, and all other electrons up to n-2 quantum number you will get 1, shielding constant as 1. Similarly for D, 0.35 from the other electrons in the same group, 1 from the electrons that are in the same n but other azimuthal quantum number, means in the S and P, and 1 from the other electrons whose quantum number is less than n. Similarly from the F group, if there are electrons in the same group, means more electrons in the F, that time you have to add 0.35 as a shielding constant. From other electrons in the same principal quantum number but different L, means in the D or sp group, you have to add 1. And similarly from the other electrons in the different quantum numbers, you have to add 1 for the shielding constant. Now we will take an example and we will determine the shielding constant for all the electrons of this iron. For this I will choose the pen. Yeah, see, so for iron this is the electronic configuration 1s2. So this is not the ideal configuration, this is actually how you write to determine this shielding constant. First you write 1s2, then in one group you add 2s2 2p6, another group you add 3s2 3p6, then you write 3d6 and 4s2. Now we will determine the shielding constant of these 4s electrons. So here we have 2 electrons. So for 1 electron if we calculate, so there is only one more electron in this 4s group, right? So from that electron we will get 0.35 shielding constant. That's why 0.35 into 1. Now from these 14 electrons, they have same n, same principal quantum number, but different azimuthal quantum number. So we will get 0.85 into 14. So this much will be the shielding constant value from these two groups, this one and this one. So this one electron, this coming from 4s, that is giving 0.35. These 14 electrons, those are coming from this 3s2, 3p6 and 3d6, that is giving 0.85 each. And we have 10 more electrons in this 1s2, 2s2, 2p6. We have 10 more electrons. These 10 electrons are contributing total 1 value. The total shielding is depicted as 1, and if it is less than 1, so that means it is not shielding totally. Okay, so if we calculate, so we will get S as 22.25. Now our atomic number is 26, so Z is 26, and if we do Z minus S, we will get Z effective to be 3.75. So 3.75 is the Z effective in this 4s electrons. Means originally in the iron, so if this is the nucleus, I will just shade it. So in the nucleus we have 26 electrons, right? Now after that we have different 1s, 2s, 2p, 3s, 3p, 3d, 4s. So we have all these electrons. Now just assume if it is 4s electrons here, and we have all other electrons here before this 4s electrons. So these 4s electrons, each electron, they will think that there is only 3.75 number of protons. So actually we have 26 number of protons. So there are 26 number of protons, and the 26 protons are attracting these electrons, but the inner electrons, they have shielding effect. So they are shielding the attraction of these protons. So that's why this 4s electron, they will think, or they will get the force that only 3.75 protons are there in the nucleus of iron. So that much attraction these 4s electrons will feel. Now let's come to the 3d electrons, and if we determine the shielding constant of 3d electrons. So for 3d electrons, there will not be any contribution from 4s. Okay, so we have to consider the electrons which are before 3d or in 3d. So from 4s there will be zero shielding constant. Now in the 3d electrons we have 3d6, 6 electrons are in total. So each electron can see 5 more electrons. So 5 more electrons, and they are giving shielding constant 0.35. So that's why we have to multiply 0.35 with the 5. So this, from this 3d6 we get 0.35 into 5, and all other electrons with the same principal quantum number and different azimuthal quantum number, this one, and here different principal quantum number, they all electrons contribute shielding constant 1. So that's why all 18 electrons before this 3d, they will give shielding constant 1. So the total shielding constant comes out to be 19.75. And if we subtract this S from the Z value, we get 6.25. So the Z effective is 6.25. So the electron which is at 3D, if the electrons are 3D, so those electrons will feel, those are much closer to the nucleus, right? So they will feel more attraction to the nucleus. So they will feel that per electron there are actually 6.25 protons. So this will be their conception. Means that will be the Z effective to these 3D electrons. Now if we calculate for the 3s2 and 3p6, these electrons, so total there are 8 electrons in 3s2 and 3p6, and this 3d and 4s will not contribute anything, so we will have 0 and 0 for 4s and 3d. Now 8 electrons are there in the 3s2 3p6, So one electron can see 7 more electrons. So 7 electrons will impart 0.35 shielding constant. Then before that we have 8 more electrons in the 2s2 and 2p6. Those 8 electrons, will give 0.85 shielding constant, and we have 2 electrons in the 1s. So those 2 electrons will give shielding constant 1. So total the S will come out to be 11.25, and if we do Z minus S we get 14.75 as the Z effective. So the electrons which are in the 3s and 3p, see here the principal quantum number is same, but as the azimuthal quantum number is different, so they will have different effective nuclear effective Z effective, different effective nuclear charge. So they will feel the Z effective to be 14.75, whereas in case of 3d electrons they are feeling only 6.25. So the 3s and 3p electrons, they will have higher attraction towards the nucleus. Now if we calculate for 2s and 2p, so for 2s and 2p, all this right hand part will be 0. So we have 0 for 4s, 0 for 3d, and 0 for 3s, 3p. So in the 2s and 2p, we have 8 electrons in total. So each electron will see there are 7 other electrons. So 7 other electrons will impart 0.35 shielding constant, and the 2 electrons in 1s2, they will impart 0.85 as the shielding constant. So the total shielding constant is 4.15. So if we calculate Z minus S, we will get 21.85. So the effective nuclear charge is 21.85 for 2s and 2p. So these 2s and 2p electrons, they will feel that this atomic number, or this number of proton in the nucleus is actually 21.85. So that much attraction they will feel. And if we consider for 1s electron, all other contribution will be 0 from 2s, 3s, 3p, 3d, and 4s. And 1s, in 1s we have only 2 electrons. One electron can see there is one more electron, so that electron will shield only 0.3 or 0.30 just for 1s. So the effective nuclear charge will be 25.7. So the electron which is very close here, 1s electron, that will feel that in the nucleus there are 25.7 protons. So this is the concept of effective nuclear charge. So this tells that in an atom, differently positioned electrons, they will feel different effective nuclear charge, and depending upon their effective nuclear charge, they will feel more or less attraction towards the nucleus. Fine. So next we will move on to Goldsmith geochemical classification of elements based on chemical affinity. So Goldsmith said that elements can be classified into 4 groups. First one is the siderophiles, means iron loving. So these metal elements have affinity towards iron and present in Earth's core in free state. They have incompletely filled outermost shell. For example, iron, cobalt, nickel, ruthenium, rhodium, palladium, platinum, osmium, iridium, and gold. Next one is chalcophiles. I'm sorry, this will be two actually. Next one is chalcophiles, means sulfide loving. So these metals tend to bind with sulfide, and their ions are soft acids. So the soft acid, this thing comes in the hard soft acid base principle, which I will teach you sometime later. So these means these ions are more polarizable in nature, and their ions contain 18 electrons in the valence shell. For example, copper, zinc, cadmium, mercury, lead, arsenic, antimony. So just a small, I will just say quickly, just wait 1 second. Yeah, from the hard soft acid base, if I have to say very briefly, You have this atom and you have this atom. Oh, my circles are very bad actually. So if you have two atoms, now in this atom, these electrons are very tightly bound. This atom size is very small and the electrons have stronger affinity towards the nucleus. Whereas in this atom, if this is your nucleus and these electrons are far from the nucleus, the electrons which are here. So what can happen if you give another atom A? Now these electrons or electron density can be polarized, can be changed like this, something like this. So this is just a crude way to say that as these atoms which are far away from the nucleus, they can be polarized or they can be drawn together, they can be deformed. But that thing will be uh, very difficult in these smaller atoms. That's why these smaller atoms are called hard, now hard atoms, and these ones are soft atoms. These bigger atoms are the soft atoms. Now the next one is lithophiles, stone loving. So these metals tend to bind with the oxides. These are hard acids according to the hard soft acid base theory, and their ions contain 8 electrons in the valence shell. For example, alkali metals, alkaline earth metals, early members of transition elements. And next, and the fourth group is the atmophiles or vapor loving. So these elements remain as gas in the atmosphere. For example, nitrogen, oxygen, inert gases. So the thing is, the chemical affinity may depend on environment too. Chromium is lithophilic in crust, but in an oxygen deficient condition, it can exist as a chalcophile. So, based upon your atmosphere or environment, your atoms can act differently. Iron is siderophilic in the core, but lithophilic in the crust. So, different atoms can behave differently according to its environment. Now, this is the periodic table which shows Goldsmith's classification based on the chemical affinity, and you can see these blue ones are the atmophile. You can see these inert gases, carbon, nitrogen. These green ones are the lithophile. You can see these alkaline earth metals, alkali metals, alkaline earth metals, some transition metals. These are the lithophiles. These ones are the chalcophiles. You can see here sulfur, selenium, tellurium, arsenic, antimony. These elements are considered as chalcophiles, and these red ones are called siderophile. So you can see iron, cobalt, nickel. So these are called as siderophiles. And some elements can be both siderophile and lithophile. So some element can be both, and depending upon the environment, their nature can also change. Next, we will discuss about the Goldsmith's cosmochemical classification of elements based on cosmic abundance. So cosmochemistry or chemical cosmology is the study of the chemical composition of matter in the universe and the processes that led to those compositions. So according to that, elements are classified into four groups: refractory, moderately volatile, high volatile, and siderophile. So you can see the color coding, and from the color coding, this right hand side you can see the color coding, and from the color coding you can see these red ones, these are highly volatile. These yellow ones are volatile, and these light yellow ones, these are moderately volatile. So for example, these inert gas elements, they are highly volatile. Now if you see fluorine, chlorine, these are volatile, and if you see phosphorus, that is moderately volatile, manganese moderately volatile, copper, gold, these are moderately volatile. Now the green ones, these are moderately refractory, and the blue ones are refractory. So aluminum, silicon, ruthenium, iridium, these are refractory. And this violet one is highly refractory. Tungstenium, osmium, rhenium, zirconium, these are highly refractory. So this is the periodic table which classifies the elements based on their cosmic abundance. So if you want to know more, if you want to know in detail about these things, you can Google these things, or you can see some lectures which are focused on this cosmochemistry. So these many things we have covered in this video. In the next video, in the lecture 6, that is going to be a very important lecture. Do not miss the lecture, because in the lecture 6 I am going to discuss all periodic trends, and I will give you details of the periodic trends as well as tricks to remember those periodic trends, and how you can remember those things, how you can explain those observations. All things I will discuss in detail. So the next lecture is going to be a very long lecture, but it is going to be super useful lecture. So in the next lecture, we will discuss periodic trends in atomic radius, atomic volume, ionization energy, electron affinity, electronegativity, metallic character, and cohesive energy. As well as I will show some tricks and notes to remember these trends. And you can see in this right hand side, I have already shown some arrows, that is actually short form to remember this periodic trend, which I will discuss in the next lecture. So do not miss this next lecture, okay? And you can comment down below if you have any confusion regarding this lecture 5, or if you have not understood anything in this lecture, you can comment down below. If I get more number of comments, I will prepare a separate video just addressing your comments. Or if you know more, if you think I'm not correct or not fully correct in any argument, you can comment down below, you can let me know. As well as if you think these lectures are helpful, please share it with your friends or juniors and let them learn. So thank you very much. See you in the next video. Bye bye.